so you get to the actual good stuff. So this is the VideoRecSys portion, I guess, of our combined workshop. And this is the second workshop on large-scale video recommended systems. And our mission is we want to bring a bunch of research managers together to talk about the latest advancements in video recommendations. And I want to call out my co-organizers, Khushhall, Amey, and Saurabh. I've done an absolutely great job putting this whole workshop together. And I also want to give a big shout out to our co-collaborators in RecSys, Arnie, Dane, Mark, and Wang, I think. Are you guys on here? Come on up, come on up. Everyone's here? Okay. Well, things went up. Some people are still reading. I don't know. But anyway, these guys did a lot of work. I know joining such was great, and you'll see it's awesome. Cool. So, why are we? You can stay if you want. So why are we doing this again, right? So one is that video consumption is a very common application. We got 5 billion people almost a week who watch video over the internet, and that's just a large. It's a large important society, and there's a lot of challenges that are still unsolved. And so, what are those challenges, you might ask? Well, content understanding involves many time-variant modalities. You got auto, visual, object detection. Users often desire novelty. We can't just recommend them the same thing over and over again. At least we can't do that and say we're doing a good job. And then, content's often new, sometimes at a very large scale. Some of this was talked about this morning already, right? And so, what are we trying to achieve? We just want to exchange knowledge, foster discussions, maybe highlight some interesting problems. So, I'll just quickly go over a few of our speakers. Ed's coming at 4:15 today. I'm pretty excited about this. If you guys can be back for this, might want to be here early. The room will probably get full. We're getting a great talk in 2 minutes about actions speak louder than words. This will be, I'm a little bit biased, but I think this is really strong work, so I'm pretty excited about this. Jiaqi will also be on the call. We have Derek going to talk at 2:15 about less is more, and Lu Fang will be talking some about inference. I've heard a lot of people on this morning with just how difficult of a problem inference really is in practice, and so I'm also very excited about this talk. And then Vito will be talking about Netflix, but specifically we focus on the live content aspect of it, and there are a lot of pretty interesting challenges there. And lastly, from 5 to 5:30, we're going to have a panel discussion with Ed, Justin, Lexi, Yueming, and Chen. I'm pretty excited about this as well. So, Chen will also be a senior director of product at Porobo, will be on the panel. So, with that, I think we can get started with our first talk. So, I wanna invite my colleague up. It's been a very successful career at Meta, and it's hard to believe we've only been there 4 years, considering how much impact we've had. We're the first authors on one of the most interesting papers I think to come out of Meta this year, and very excited to hear your talk. So.
Okay, thank you everyone for joining today. My name is Yueming. I'm a software engineer and a model recommendation system. Sorry about that. My name is Yueming, and I'm a software engineer in the model recommendation systems team at Meta. So today I'm going to introduce our recent work for developing the next generation recommendation systems with vertical recommenders here at Meta. So this project is a collaborative effort involving many of my colleagues working together, and I'm very honored to represent them in this presentation. Okay, to begin with, as Jensen remarked in the NVIDIA earnings call in 2024, that recommendation systems are the single largest software engine on the planet. And we're proud that we have been working on building and improving this software engine at a 100 times larger scale as of today. So first, a very high-level introduction to this work. that we're presenting today, we have developed generative recommenders that reinterpret main recommendation tasks within a generative framework. And through combined efforts in modeling and infrastructure, we have achieved significantly improved training efficiency and inference efficiency along with model performance. And as of now, this work has been put in production across all of the major recommendation products in Meta, bringing substantial boosts in business metrics. Additionally, for the first time, we have been able to demonstrate the scaling law in the industrial recommendation setup. So we will start by giving an overview of the two key backgrounds, which are deep learning recommendation models, or DRMs, and generative models. So for nearly a decade, the DLRMs have served as the core of industrial recommendation systems, fueling the engines behind the recommendation platforms of major tech and e-commerce companies. So the diagram displayed on this slide is from the well-known YouTube paper for YouTube recommendations that was published in RecSys in 2016. So DRMs are characterized by the usage of heterogeneous features and architectures. The features that were typically used in DRMs include numerical features such as content and ratios, and embedding features such as creator and content embeddings, categorical features such as post IDs and creator IDs, and sequential features such as a list of post IDs and the users have previously interacted with. So, given that a huge amount of new contents are added into our recommendation systems in every single segment, some feature spaces like the post IDs and creator IDs, they can be of huge scale. Like for instance, they can often reach into the billions. So to effectively manage and utilize tens of thousands of such features in DRMs, so the DRMs really consist of various neural network components to do feature transformation, feature interaction, and intermediate transforming intermediate implementations, and compose a final output for the multiple different tasks. And over the past decade, there have been continuous developments in the architectures and capabilities of the DRM space. For instance, feature interaction architectures like FM, DCN, DTN, and task arcs like MLOE, sequential submodules such as DIM or SIM, debalancing arcs or retrieval architectures beyond 2-tower settings like deep retrieval or TBM, etc. Now let's shift a bit to the generative models, in particular large language models. So with the huge success of large language models, nowadays people today are extremely interested in how to use generative models to help boost the performance of our recommendation systems. There have been a lot of such attempts, and some examples include, for instance, works like LM Rank, which tries to use LMs as a zero-shot rankers, and also Note LM, which tries to do transfer learning utilizing the word knowledge in LM to help with recommendation performance, like to use them as retrieval generators. So we have advantages from both LMs and DLRMs for recommendation systems. So the advantages from LMs include being able to replace manual feature engineering and incorporating word knowledge, which are particularly beneficial for closed-out scenarios. And importantly, it scales very well with compute. And the advantages of DLRMs include leveraging a vast number of features, human engineered features, and also it's based on very concise representations that are efficient and capable of supporting extensive context sizes. And also it scales with in-domain recommendation data. Okay, but when you think about this, should we build our next generation recommendation systems solely based on LLMs? So while LLMs have a lot of advantages, there are also several challenges that we should consider. So first, the word knowledge that inherent in LLMs, they primarily benefit closed-out scenarios. And at the same time, substantial effort is required for LLMs to outperform established collaborative filtering methods, even on simpler datasets like Nuvida's 1 million. So the table on the right comes from LLM-Ranker paper, which reports the best NDCG metrics on the Nuvida's 1 million dataset. As far as we know, until May 2024, we can see that there is still a significant performance gap between this approach and traditional approaches, DRM approaches like Saurabh. So additionally, tokenization needs to be orders of magnitude more. Okay. Additionally, tokenization needs to be orders of magnitude more efficient for LLMs to replace DRMs. So DRMs really need to handle context lengths in terms of the number of post IDs that the users have previously interacted with, ranging from 10K to 100K, quoting from Khushhall's KD 2022 twin paper with a required response latency of only tens of milliseconds. Okay, so building recommendation systems solely based on LLMs is hard. Then what about the deeper integration, like building a generative DRM? So there are also fundamental differences between these two frameworks as we explore a deeper integration. First of all, in the industrial recommendation world, we often have thousands of features that lack explicit structures. We also have huge and dynamic vocabulary space, as we know that new contents will keep adding into the recommendation system every second. So we have billions of vocabularies that keep changing continuously. And this is very different from the 100K scale static vocab assumption of LLMs. And finally, of course, we need to consider about the cost. So large models really need to utilize huge amounts of training data. For instance, GPT-3 is trained with 300 billion tokens, and Llama 2 is trained with 15 trillion tokens. Okay, this number sounds impressive. Well, at least by LLM standards. However, as those of us in this room knows, they might not seem as remarkable when compared to the scale at which our recommendation systems operate. As our systems can easily generate 10 times more tokens in just a single day. So with all of these considerations in mind, here comes our solution. We build our next generation recommendation system with generative recommenders, and we call it GRs. It is a novel approach that combines the best of DRMs and generative models by rethinking the formulation of fundamental design choices in DRMs, from feature engineering to model architecture design to addressing the computational cost challenges for both training and inference. So let's begin by take a step back and look at how recommendation systems have historically utilized sequential informations. There were numerous academic research articles like Dharwadker that have introduced sequential recommendation models in the past. Typically, these models predict the next item that the user is going to interact with based on the previous items that the user have viewed. This is more similar as a retrieval setup. On the other hand, in the industrial world, sequential information is often used in submodules within DRMs, such as DIN, BST, or SIM. These submodules typically utilize target-aware attention to predict the actions that the user is going to take on a target item based on all the previous items and the candidate item itself. This approach aligns with the standard RecSys. It is important to highlight a significant expressiveness gap between the academic setting and the industrial setting of using sequential models in recommendation systems, which is the features, more features. In the academic context of sequential recommendations, the model typically only features a simple sequential architecture that with only one ID feature, that is the item ID feature. And in contrast, in DRM setting, the number of features often scales to a few thousands or even more. So this makes feature interaction a primary field of research for DRM. So how do we close the gap between the academic research and the industry application of sequential models? The answer is quite simple, that cross attentions. So target-aware attentions have been already widely adopted in sequential submodules in DRMs, as we realized, and we realized that we could leverage them to extract the cross features. However, there's still a scalability issue. Target-aware attention requires the traditional impression or target-based setting, which slows down training by a factor of 1. And consequently, the commonly used target-aware attention module in DRMs are really pretty simple architectures. For instance, pairwise attention with only 1 to 2 small layers, resulting in limited model capacity. Okay, now I can talk about how we design our generative recommenders that get the best of DRMs and generative models while addressing these candidates mentioned. So first, we build a unified answer for each user as a pure representation. So we interleave items, including items that the users have interacted with, and the candidate items that the model is predicting. And the corresponding actions that the users have took on those items in the past into a single unified segment. The figure on the right-hand side is an illustration of this single unified segment. And in this way, look at it in a higher way, based on an item token, we can predict the action that the user is going to take on this item through target-aware attention, like a standard ranking setup. And based on an action token, we can predict the next item that the user is going to interact with, similar to a standard retrieval setup. So in the next step, we insert all the categorical features. We insert the categorical features as slow-changing time series into the unified settings. For numeric features, there are generally constants or ratios. For example, one feature could represent users' past CTR over a certain over the items matching a certain topic. An important observation is that the categorical features, for instance, item topics or locations, that we use to aggregate those numeric features are already sequentialized in our unified segments. Hence, we can remove most of the numerical features in GRs, given that a sufficiently expressive sequential architecture coupled with a target-aware formulation can meaningfully capture numeric features as we increase the overall sequences and compute in GRs. So with these changes, the final model architecture will be a fully sequential model with a simple task arc. As a result, we were able to address expressiveness constraints that we mentioned earlier in the talk to enable fully sequential ranking models in industrial setting, and thus close the quality gaps between academic research and industrial DRMs. And even more, the design is very friendly to compute cost. While, and we will share more details about this in the next section. GR's new formulation greatly improves model quality. For instance, in one of the billion user recommendation products at Meta, it brought around 4% to 12% online metric rate across different business tasks. Besides GR's model formulation, which brought us significant quality wins, we still need to handle the compute cost for processing at order of magnitude more tokens than LLMs per day. So how can we make this model run faster? In this section, we will introduce how we speed up training by 10 times and inference by 900 times through model and infra code design works. So we start with HSTU, our encoder design, which has better model performance in recommendation scenarios than vanilla transformers and runs 15 times faster than transformers. So first, HSTU adopts quantized aggregated attention rather than soft-max attention. Second, we fuse our self-attention and MLPs via element-wise gating to reduce compute. Third, we leverage and algorithmically reduce sparsity. We implemented improved GEM kernel extending memory efficient attention and flash attention to leverage sparsity. We also implemented algorithms like stochastic lengths to further increase the sparsity of the sequences, reducing the complexity from O(n) squared to O(n) to the alpha, where alpha is a configurable parameter. Our experiments show that HSTU outperforms transformers and area space lines on synthetic public datasets as well as industrial GL settings. And additionally, it scales up to 15 times training. Additionally, it achieves up to 15 times training speed on the 8K length sequences, and thanks to the optimizations from previous slides. Next, I'll talk about how to get inference for free. Well, almost free, by achieving 900 times speed up for GR compared with DRMs via N5 algorithm. So I think that we have a great joke about Star Wars on the slides, but I'm not actually good at telling jokes, and I don't have a lot of context about Star Wars, so I'm going to skip this slide. But here's an injected advertisement. So we're going to give another talk about this work in the generative models in recommendation workshop on Friday. So my colleague Jiaqi, who's the main author of this work, is going to present it as well. So if you are interested in hearing about it, you are most welcome to go to the talk on Friday. Thank you. Here are the key insights that's powered in Python. So as we mentioned before in the model architecture section, the item tokens, which include past items that the users have interacted with, and the candidate items that the model needs to predict, are all put into a single unified time sequence. And this enables batch inference, which can be directly applied to target-aware autoregressive settings and maximizes compute sharing. That is to say, we only need to run the forward path of HSTU encoder once to get the prediction for all the candidates. And then the complexity roughly changes from like O(n) squared times number of candidates to O(n) plus number of candidates as well. And additionally, micro-batching further scales up batch inference when the number of candidates reaches a larger scale, like 10K. Moreover, encoder-level cache or KV cache further reduces redundant operations between micro-batches and can be applied even across requests. So, how well do these optimizations work? Let's start by evaluating batch inference. For a small number of candidate sizes, up to hundreds of thousands, with a like if we use the 1x flops DLRM model as baseline, we could enable up to 1.5 speed up for a 300 times more complex GR model. Next, let's look at micro-batching with KV caching. So this setting is suitable for cases with larger number of candidates, like 10K candidates. With the 16K candidate size, the micro-batch and with a micro-batch size of 1K, with KV cache, it brings additional 2x inference QPL speed. So combining everything together, we are able to serve a roughly 300 times more complex GR model with 3x QPLs. And that's how we get the 900x speed up versus DRMs. Okay, one more thing. So far we've been focusing on the generative recommenders for ranking. So how about retrieval? It's commonly believed that dot product methods like two-tower models, dual encoders or similar methods, and their variants are the only approaches that scale to large corpus for retrieval problems. In this particular setting, the inference can be done very efficiently using something called maximum inner product search, or MIPS. MIPS basically means that given a set of embeddings, we want to find the embedding such that the inner product of this embedding with our query embedding is maximized. So what is the problem in this formulation? The first thing we might ask is dot products expressive enough? So from the table on the right-hand side of the slide, rank analysis show that real datasets, even public benchmarks as movie are high rank. Whereas in a two-tower setting, the the maximum rank of the model cannot exceed the invented dimension plus 1. So how can we enable more expressive models for retrieval? So our solution to this question is a new class of non-similarity functions called mixture of logits. In mixture of logits, we define non-similarities as an adaptive composition of elementary logits. In the equation on the slide, we have p individual elementary logits, and pi performs adaptive gating per user item pair. This allows us to construct high-rank expressive models efficiently. This approach outperforms baselines with a significant margin on public datasets and is also validated in production settings and both meta and linking. You can check the related paper for more details if you're interested. At the same time, it still remains efficient and interesting. Okay, now putting everything together, we will further explore the scaling property of GR. So historically, the compute growth of RecSys models have largely lagged behind other fields. Many deep learning models, like especially LLMs, benefit from scaling law, where losses exceed scale as the power law of compute. Nevertheless, DRRMs generally scale with data or features, but less well with compute. In GR, we have enabled fully sequential models in industry setting for the first time. So GR is capable of catching long-term interest, target-dependent interest, and short-term interest in a single unified sequence, and representing sparse features as slow-changing time series in the sequence. So while learning numeric features through target-aware attentions as a replacement for the heterogeneous features and architectures in DRMs. And combining everything together, GR, which is the blue line in the diagram, demonstrates good scaling properties compared to DRMs, which are the red line in the diagram, especially in the high compute region. To give you an idea of the numbers on the curve, normally a 0.5% increase in case rate or a 0.1% reduction in NE means represents significant improvements in our systems. We observed this phenomenon up until the largest models that we were able to test, which consists of 8,000 sequence lengths, 1,000 embedding dimension, and 24 layers of HCU, at which point the total amount of compute we used in this model, if normalized over 365 days, as we use the standard streaming training setting, is close to the total training compute used by GPT-3 and Llama 2. So GR brings huge online business metric wins on the largest recommendation products and meta, enable 100 times more complex models while saving inference resources at the same time. To conclude our talk, the generative recommenders for GRs reinterpret the main recommendation tasks with a generative framework, unifying heterogeneous feature spaces with, while addressing expressiveness constraints in the traditional settings. With up to 15 times training speed up and compared with transformers, and additionally, MFICON enables a 900 times speed up versus DRMs and inference time. And HSTU-based GRs with 1.5 trillion parameters improve online metrics on many products by a maximum of 12%. We further observed scaling law in industrial scale recommendation systems for the first time. Please feel free to download our papers if you want to know more about this work. We're also hiring across all levels in case you're interested in building the next generation recommendation systems with us. And in addition, we're going to give another talk in the RealGen workshop on the Friday, and then Jiaqi, who's the main author of this work, will be the speaker. You are welcome to attend if you'd like to hear more about this work. Thank you.
Transition from traditional VLRM to GR paradigm, and that's around cold start and exploration. Do you have to do anything different to address cold start in a generative recommender problem formulation than you do in VLRMs? And likewise, I'd be interested in your thoughts on a similar question about exploration. Thank you.
Yeah. I think in addition to the stuff that we're talking in the slides, we're also doing content augmented sequential modeling. Like for instance, trying to portray from raw pixel level with the post ID sequence in our models. And I think that help with post-up problems.
Okay, thank you very much.
This is someone right.
I think one compare with the thanks for the talk about. Compare I think with the way that the paper organized the data with the morning sessions when Dimitri talked about their ways of building a long-term model. I noticed that one small difference is that you take both positive and negative actions into the sequence, where I think Dimitri take both of the positive examples. So one question here is when you unify these, unify sequence between both the stable and relative models, do you notice any pressure down to the diversity in the downstream? Because I assume that this will probably bring some similar inputs from your using interactions and bring some diversity challenge.
If I understand correctly, there are maybe two parts in this question. The first one is how we handle negative events in the sequence. The second one is how we handle diversity problems for retrieval settings. I think for the first question, as we mentioned that we interleave items and actions in the unified sequence. So in addition to the item token, we also have action token that to represent the actions that the users took on those items. So if the users took negative actions on the item like skip or dislike, so that will be also represented with the action represented in the action representation. So in this way, the model can learn to distinguish between good testers and negative testers of the users. The second problem is how to do diversification in retrieval setting. I think it's actually a universal problem in retrieval instead of just for GR. So I think we have a lot of related work on it. For instance, we do stochastic policy when we draw candidates from the retrieval distribution, and we do diversification post-processing algorithms after the retrieval layer, for instance.
Thank you.
Yeah. Just time for one more.
Yes, so I have a question. Sorry, I have a question. So about the dense part model parameter size, what's the biggest part, biggest model?
Okay, I think the model has 1.5 trillion parameters in total. Most of it are from the sparse arc, the hashtag events. And for the dense part, 99% of it is from the HSC encoder.
Yes.
We have stacked 12 to 24 layers of encoders, and a small percentage of it is in the taskbar.
Okay, so I think the data parallelism is enough for the dense part. You don't need to do tensor parallelism or compact parallelism for the HSQ dense part training.
Not in the published version of this paper, but that's definitely a next step that we're working on. While we are continue to scale up the model.
Okay, I mean you said you already make the model online, so for the online model parameter size doesn't really use tensor parallelism right now.
I think that's different. Are we talking about FSDP or related?
What?
Are we talking about FSDP or related?